this semester. Yeah, okay.
TypeScript is
Hi, thank you for
interesting.
coming. Covering password cracking if it wasn't obvious. First I'll go over some announcements. What are you laughing at? What did I do wrong? I was told to put OC Gaming CTF on here by now.
True.
We are doing OC Gaming CTF, but first, Tracer Fire. There's this cool forensic space, like weekend-long competition, held by the National Laboratory of India called Tracer Fire. And that is going to be, it's on like the 22nd, 24th, that rough weekend of March. We don't have signups for that yet, but I want to get you all excited about that because it's a cool event. We're going to be helping run it.
22nd.
Yeah, 22nd. Okay. So if you're interested in getting a little more like blue teamy forensic experience, I know we mostly cover like CTF, like attack based stuff. That's a really good competition for that.
Have to learn how to guess.
We are playing OSU Gaming CTF 2024. Yes, that OSU. Hi, man. Hi, Jordan. Okay. It's a rhythm game themed CTF, and that's gonna be this weekend. And we're not gonna be running a Sunday meeting. We're just gonna be chilling, doing that. I guess studying for midterms. Should be pretty chill. Oh, this is the flag for this week. It should be under the tracking category. So yeah, I'll give you like a minute to get that submitted. In the meantime, I think I'm handing this off to you.
Of course.
Yeah. I'll make sure that you're visible. Yeah, you're good. Yeah.
Pretty good comic.
True.
Let's try them all on Venmo.
We love Venmo.
All right, so to start off, we're gonna discuss a bit about what hashing is. So you've probably seen a couple of things within your browser certificate that represent the fingerprint. And that's kind of an example of something that can hash. So basically a hash is just a one-way function, which means you can't go the other way around and reverse engineer the string that you hashed. And it takes in something that's currently in plaintext and generates a garbled fixed collection of bytes. So for example, if I give the plaintext hi, and I say, put it through an MD5 hash function, it will generate this kind of mess. And if I put something like I with an extra I, the hash is going to be completely different because we don't want to be able to like trace back what the original plaintext was. And even if the plaintext is very long, because the hash is safe, you can see that the corresponding hash is still the subject collection of bytes. In this case, 16. So the way to keep security. So as for the relation of hashing to passwords, as you may know, it might not be the best idea to just store your passwords in plain text on a database, because everyone's going to see it then, and it's just going to be active. So when you log in with a password, you kind of hash the password up, and that generates the fingerprint, and then the internal system will check it with whatever it has in store. For example, the server here will store the hash 5, 4, and so on. And if the client guesses hunter 2, which is not the password, the fingerprint that hunter 2 will generate, as you can see, it's different. But afterwards, if it gets password, it's going to generate the MD5 hash for any other hash function. And it's going to be the same 5 string. So we can instead check hashes instead of plain text hashes. So if an attacker obtains a hash, because hashes are one way, we cannot actually obtain the password. We only obtain that hash. So it's more safe against stuff like database attacks. But it's not exactly entirely safe. For example, there are ways to actually crack password hashes, and that's what we're going to talk about today. So as mentioned earlier, hashing is one way, so you can't really get the password given the hash, but that still doesn't mean that it's impossible to do. In fact, the only way to efficiently get it, given that all security considerations are met, is that you can only brute force it. And the main way to do it without any kind of like context beforehand, that's called a blind brute force. That's by using every possible combination of numbers and symbols. And this could take a really long time. For example, for the more used hash algorithms like SHA-256 or SHA-5, this could be on the order of 2 to the 5 different combinations. And that's more atoms than there are. That's more than the number of atoms in the universe. So it would take a very long time. However, if you're giving information beforehand, you can actually use the structure of the plain text that you're given to be able to compute a set of hashes quicker, because hashes are always determinants. And so you could do something like a dictionary or a word list attack if you know, like, say, the password is of the form 7 letters and 1 number at the end. You could generate a word list that has all possible combinations of 7 letters and 1 number at the end. And that could reduce your search space much, much more and make it effective. And another thing could be rule-based dictionary attacks, which kind of like enumerate a lot of set of rules that are used for debate word lists. And this makes it a little more versatile than just a purely word list. So computing hashes is a pretty big problem that's currently been, we're currently making a lot of strides in, especially with the HPC. So computing hashes, like a single hash, takes less than a second, but because a lot of like hashes work on the space of like multiple bytes or like a large amount of data, computing a lot of hashes to go through every possible combination will build up and take up a lot of time, as I said before. So as a result, being able to crack passwords and be able to find the hash could take a lot of compute power. Now, a lot of hash computation is just repetitive work of checking and blacklisting if you see that combination. So as a result, you can make a lot of parallel threads, find different combinations of hashes and blacklist the ones that don't work, and you could cover much more ground. So for this reason, GPUs are way more effective at cracking hashes than CPUs, and your hash rate can sometimes be like 10s or 20s or even hundreds more effective than this CPU. And people build a lot of custom passive cracking rigs with lots of GPUs strung together. You'll see this in a lot of like efficient Bitcoin mining rigs. And they could also just run the high compute cloud server on AWS. A very common hash computing framework that's now becoming more and more popular is the ASIC, which is a chip that's implemented on hardware specifically for cracking cancer. So a lot of people are finding crazy ways to activate hashes. But most of the time when you're doing challenges, you could use something like Google Colab's GPU, a high compute cloud server, for which you might not need to pay that much money for. Depends on the hash. All right.
Yeah, I can. Happen.
Yeah.
Okay, so over time, there become some popular word lists that people like to use. They're common for like CTFs and stuff because you only have like 2 days to do those. So they don't want you to spend your whole time just trying to crack passwords unless there's like a specific strategy they want you to use. So a big one's Raku.txt. Once upon a time, there's this company called Raku. They got breached. All their passwords are in plain text. And ever since then, this big text file called Raku has been updated to include the most common passwords. And so that's a very common one you'll see. Another common, like another repository that has a lot of pre-built word lists is SecList, if you're interested in looking into other options. Oh, wrong one. Now, if you know stuff about the person that you're cracking the password of, you can usually kind of narrow down your options. Like, let's say you're trying to crack my password, and you know I really like Taylor Swift. There's some text files you could go through. There's some lyrics you could put in there that would probably increase your probability of getting my password. And like, the more information you know about someone, the type of stuff they might make their password, the more likely that type of thing is to succeed. That's also why it's important to like have more random passwords and not like just do like a Taylor Swift lyric.
As a result, this is also why sometimes it might not be the best idea to have like a bunch of seemingly random words within your password, even though a lot of people in the past thought that was a good idea. And that's because of the fact that you can make custom word lists of commonly used words that you might actually use in context. So,
True. Like you're talking like about like passwords, right?
yeah, passwords.
And there's some tools that make it a little bit easier to build those word lists, like Mentalist and Hashcat rules, which we're gonna go into a little bit more later. There's a lot of different hashing functions. Some of them are better than others. Some of them have just aged because the better that technology gets, you heard what Sagnik was talking about. There's some GPUs are getting better. There's some crazy stuff going on. And the better we get at computing brute force, the basically better our hashes have to get. So on like older systems, you'll see different things than newer systems. Not all hashes are created equal. So yeah, this is a lot of what I was talking about. The bigger hashing sizes are going to reduce your possibility of hash collisions. So for example, a lot older of a hash MD5 only has 16 bytes, but SHA-512, which is used on a lot more modern applications, has 64 bytes. So that's going to take longer to find a collision for. Another strategy. Oh, hi, George. Yes.
Hello. Given that there's been a cryptographically secure, unsecure hashing algorithm, how would one prove that if someone says, okay, this algorithm is cryptographically secure, obviously there's going to be collisions, but how would you prove that a hashing algorithm is secure?
So while collisions for different hashing algorithms may exist, the question is how fast can we actually find those collisions? So normally we would consider a hashing function to be insecure if we could construct some sort of like specifically probabilistic polynomial time algorithm to be able to find collisions. However, even if your algorithm is able to find collisions, if it does it within exponential time and your hash function covers a lot of space, you could generally consider that to be secure. That's what we call collision resistance.
That's a good description of collision resistance. Thank you.
Yes.
Yeah, there's a lot of cool research out there about like cryptography and like secure, like how to prove things are secure like that. That's worth looking into. It's probably a little outside the scope of what we're talking about, but it is pretty cool. But right, one way that you can increase the security of your hashes is by solving. For a little bit of background, let's say that you regularly compute hashes for some reason of just like maybe you like forcing passwords a lot, so you compute hashes a lot. So instead of like computing those every time, you could go store those in like a lookup table or text file or something, and then like reuse those, and that would decrease the amount of time it takes to compute hashes and crack passwords. That is what salting protects against. We don't even care if the salt is public information. In fact, it probably is public information. The important thing is that it is hashed with the password. And that means that if someone is regularly like computing hashes for passwords, then they can't use those old computations, like they can't use those stored computations, like those stored hashes to figure out your password. Because like we were talking about at the beginning with the avalanche effect, even if we included like one character salt, that would heavily change what the hash ends up being. And so that just increases the amount of brute force that an attacker might have to do. What's up?
So what stops you from, like, if your solve is like this long,
Yeah,
what stops you from creating a separate table for every possible solve?
nothing is stopping you from doing that. The general idea is that everyone would have a different salt, so then you would have to recompute hashes for all those different salts, which would just be very computationally time intensive.
So like from one single password, multiple other passwords that are possible could stem just from the fact of
Yeah.
having a fixed length solve.
Yeah.
So it becomes a lot more space that you have to look for.
Yeah, so like you could still brute force a password with a salt. Like absolutely, and you should still like make your password good if you have a salt, but it'll make the odds a little bit better for you. Now we have a lesson in the hashes featuring Microsoft. This is an old hash called LM, and there's a reason we don't use it anymore. But let's just go through the steps. So step one, convert all the characters, all the alphabetical characters to uppercase. We are going to pad that password. Exciting stuff. We're gonna pad that password to 14 characters, with no characters. We're gonna split the password into two 7-character chunks, create 2 keys from those chunks. Then we're going to encrypt the string with the 2 chunks. That string specifically. And then we're going to concatenate strings, and that is our hash. Does anyone see any problems with this? I'll start here.
So you have like 2 separate 7-character chunks that
Yeah.
are being preserved in the output, so it's like effectively brute forcing a 7 character.
Yes, that's a big problem. Yeah.
Like,
What's up?
like, what is the DES encryption algorithm? Is it like more than in any shape or form? I suppose it's not, but.
It's AES at home, basically.
Oh.
Yeah,
It's supposed to be a kind of permutation of a bunch of like seemingly random characters to make a goblin mask. But as it turns out, the permutation itself is not very secure, and it is possible to crack it. So that's another big problem. Don't use DES.
that's another problem. Okay, so as you can see, yeah, it literally is exactly what you described. You are just computing every 7-character password combination. And then you're comparing the hash. And like, not even to mention, like, we're limited to, like, they're all uppercase now. There's no lowercase. We halved it basically, the amount of things we have to get.
So again, this is another curious thing.
Yeah.
For the passwords that are hashed with LM hash, it doesn't really matter in what case that you're putting the password in. It's just gonna work.
Yeah,
Hmm.
it does not matter. If you know, like when your favorite social media apps like use at least one uppercase character in your password, they Microsoft said no. Microsoft said no. We're not doing that today. Now we're gonna talk a little bit about some of the tools you're gonna use to crack these passwords. Hashcat is a brute force password cracker, quote unquote password recovery tool, I guess you could call it. And yeah, it automates all the processes we were talking about. It has a lot of options for the types of hashes you can crack. There's a couple switches you should know about, which are, well, choose your hash type, and so there's a lot of modes. If you look at that link, you can figure out exactly what mode you're talking about. You just want to look at your hash and kind of see how it's formatted, and it'll give you some hints. Then there's also choosing the attack mode. For a lot of our challenges, we're just gonna be using 0, which is straight mode, but that's where you're gonna be like looking at like dictionary tags, etc. So take a look at those. There's a couple options there that might be useful or less useful depending on what you're looking for. And then. Oh, there's always very useful. It's always good to know how to find it. Alright, so here's some examples of how Hashcat is used. I'm gonna just leave those in for reference. Those will be probably more useful to look through when you're doing the challenges. But yeah, just to get you like familiar with what Hashcat commands. And remember that we have these slides up, so definitely go back to them when you're working on the challenges. There's also a similar-ish tool called John the Ripper. Personally, we recommend Hashcat just because it's faster in a lot of cases. But John the Ripper has its own things going on. It has a lot of like exclusive tools that Hashcat doesn't have. So for those things that Hashcat can't do, John the Ripper can be a good tool for that. Another, like an example is zip to John and PDF to John. Those are good for like when you're working on password enforce zip files and PDF files. And then you can use the example hashes for Hashcat to then use those hashes you get from there to get those to figure out how to use that in Hashcat. I know you for next for mentalist.
So, mentalist was kind of briefly mentioned when we were talking about creating legends or custom web lists, but it's a very easy to use GUI program to be able to like append numbers and characters or even permutations of other word lists to already existing word lists. So if you have like a basic word list like Locky.text and want to like examine permutations of it, you could very easily put the existing word list through mentalist and generate new combinations of passwords control. So this is able to like cut in your search ability, and you could go through a lot of more passwords than as far as and this is a very common tool to be able to like cascade with things like Hashcat and John the Ripper. So I highly suggest looking through this. And then the last tool is PDF Rip, which is specifically for PDFs that I've found. And yes, for every Rust head, this is written in Rust. So it's good. But yeah, it's multi-threaded and it kind of works in a very similar form to a Hashcat, as you can see in this demo right here. You're able to give it like word engines like Alice 139, which is a tool, and you're able to back password block PDFs in a very good time, as you can see here. Another great tool to learn.
Do you know anything about the performance of this compared to Hashcat?
I think it's rather.
It's written in Rust. I don't know if you heard.
It's written in
I
Rust.
shouldn't have even asked.
Sorry, continue.
But in general, it's mainly kind of block the PDFs, but you could probably like use the Rust libraries inside to extend them to files.
Or like, is this, like, why would you prefer this over using Hashcat, I guess?
I write in Rust. But either way, any kind of like multi-threaded tool in general is pretty.
But doesn't Hashcat use CPU?
So,
But it's written in Rust, I mean,
so does PDF.
Hashtag do your own research.
So you can see kind of like, there's probably a lot more. Ever encounter a specific challenge and
Yeah, if you find a cool password cracking tool that you want everyone to know about, let us know and we'll add it next year.
let me know if it's written in Rust.
Let him know if it's written in Rust. Yeah, this is, sure, yeah.
I do questions.
Oh, yeah, questions that we didn't cover. Anything? Very cool, okay. All All right, so. Hope that y'all have fun solving the challenges. Like we were talking about this Friday, OC Gaming CTF. Next Thursday, Henry and Pete are gonna be covering the Mixolydians, I believe. That's still accurate.
Yep,
Cool,
I
okay.
thought it's gonna be much later, but then, no, we're doing this.
Henry's been caught off guard. Well, by next Sunday, we're gonna be at break, so have a good break, take a rest. Hopefully you don't have too much to do during that break, so. Yeah. All right. No talking all day.
This is my.
Yeah.